Okay. Hi, everybody. Just to let you know, I've clicked record on this talk. If you feel like you wouldn't like your name or image to appear, you feel free to write your question in the chat window, and we can take that up at the end. So it's my great pleasure to reignite the Neuro-Symbolic talks. As I was just even a few minutes ago, we had run this for a year and we had hiatus for a year, and now hopefully we'll have more again in this year. So Steve Muggleton, in case you haven't known of, if you don't know of him, he's perhaps one of the key players in the field of inductive logic programming. He's had significant contributions to the integration of logic and learning, and organized many scientific conferences around this, and lobbied for scientific communities to support the integration of logic and learning. And I suppose at this stage we're seeing finally these results come together, now that we recognize that neural networks, although they have been promising, they do suffer from a lot of key properties we'd like these systems to have, including the ability to reason from domain knowledge. So I'm very happy that Steve Muggleton is the inaugural speaker for this reignition of the series. So Steve, feel free to take it away whenever you're ready. Feel free to pop your questions in the chat window. What we'll do is we'll wait for Steven to finish his talk and then answer the questions at the end, if that's okay with you, just so that we can keep the flow. Thanks everybody for attending, and thanks Steven for accepting.
Thank you very much. So what I'm going to be talking about is the question, are AI's key challenges solved? Which may sound like a rather odd or even obvious question, but let me explain why I'm asking this question. Okay. Something's gone wrong here. Okay, let's look at the topic of artificial intelligence in 2024. Okay, so there's been a great deal of interest over the last couple of years in large language models, and one of those, ChatGPT, has been particularly prominent. For those who might not have been aware of this, these are trained on text from the World Wide Web. And they demonstrably answer questions effectively across many topics. So this is a really exciting breakthrough, and one that has ignited a question which people have been wondering about for some time, which is, at what point do we pass the Turing test and be able to faithfully claim that modern systems actually are able to achieve artificial intelligence of the kind that Turing designed that test, Alan Turing designed that test. In fact, already you can find on the web informal claims that ChatGPT does pass the Turing test. Actually, Turing's name for this test is the Imitation Game. You can find more details about what Turing's motivation and ideas about this were in his 1950 paper written in the journal Mind. It's a philosophical journal. So the question is, are there still unsolved challenges? I mean, so even if we decided that we're going to accept that the Turing test has to some degree been passed, then we should really be then asking as scientists, what is beyond here? What are the things that we still can't do? And I'm going to claim in this talk that one of those a big set of challenges exist around the possibility of AI systems which invent or discover novel entities and relationships which explain new observed phenomena in science, engineering, and mathematics. So you may be wondering, what am I referring to here as that, and maybe why do I not think that this has already been solved by systems such as ChatGPT? But let's first look at two of the founders of artificial intelligence. So if we want to really know what was intended for this subject area, these are key people to consider. So Alan Turing, born in 1912, died in 1954. In that relatively short life, did an amazing amount. So not only did he introduce or prove key theorems about the undecidability of certain mathematical functions, but he then, as part of that proof, devised the notion of a general purpose machine, which can be programmed, what we would now think of as a computer, and went on very shortly after he'd completed his thesis to work at Bletchley Park in the UK to build machines of this kind, which were the predecessors of modern computers. These were successful in decoding tasks, and they were followed up by him shortly after the Second World War in the paper that I mentioned, because a lot of the discussions that went on at Bletchley Park at that time among the cryptographers were, in their lunchtime spare time, were about how difficult it would be to make such general purpose machines do challenging tasks, such as play chess. Turing wrote a number of papers, and probably the final one of which is the 1950 paper, in which he was trying to deal with the questions that were asked by various different communities, whether they were philosophers or from a religious background, whether or not machines could be intelligent, even in principle. And it's in this context that he came up with the Imitation Game, which we now know as the Turing Test. This is a game in which a person is allowed to ask questions of a machine and doesn't know whether or not the answers are coming either from another human being or from the machine. The degree to which they could be unable to guess that accurately would then demonstrate the intelligence or the equivalence of intelligence of the machine and the human. So later on, I mean, John McCarthy introduced the term artificial intelligence. The whole idea of the test was, the Turing test was to introduce this idea and show the test that could be made to decide whether it could happen, and possibly also to suggest ways in which it could happen using machine learning. But McCarthy used the term artificial intelligence for a workshop that he was holding, in which he brought people together to discuss these things in the US. So it's really worth looking at what these two important pioneers said about the topic that we're looking at here, about what is beyond the Turing test, basically. So I'm going to take you to a section of the 1950 paper in mind that Turing wrote. This is the section 7, and it's the same section that the Turing test is described, but it also describes something that is beyond what would be expected of a machine that could pass the Turing test. So Turing talks about this in terms of supercriticality, which was a term that would have seemed natural at the time, given all of the work on atomic chain reactions around about this time. And he used this kind of as an analogy. So he says here, One could say that a man can inject an idea into the machine and that it will respond to a certain extent, and then drop into quiescence, like a piano string struck by a hammer. An idea presented to a subcritical mind will, on average, give rise to less than one idea in reply. A smallish proportion are supercritical. So he's trying to distinguish here, I think, the simple act of being able to reasonably accurately answer questions that are posed, say, in the Turing test, from something that goes beyond that. And he gives a taste of this by saying, an idea presented to such a mind, the supercritical one, may give rise to a whole theory consisting of secondary, tertiary, and more remote ideas. Arnold's mind seemed to be very definitely subcritical, he claims. Adhering to this analogy, we ask, can a machine be made to be supercritical? So this is, I think, his attempt at that point to say there are things beyond the Turing test. Okay, so let's look at McCarthy. So McCarthy, at a much later time, so actually both of these were, so Turing's statement was 3 or 4 years before he passed away, and this is McCarthy's statement close to the end of his life. And he also talks about these kind of longer term goals. In particular, he talks about a goal which he calls appearance and reality. So he's talking in a paper that he presented at the Inductive Logic Programming conference in Spain in 2006. And McCarthy says some scientific discoveries like Galileo's, here are the acceleration an acceleration equation involving discovery the relations between known entities. Then he talks about Patrick Langley's Bacon program did that. Okay, so there have been systems that can discover things in science. And he talks about John Dalton's postulation of atoms and molecules made up of fixed numbers of atoms of 2 or more kinds, and says this was a much more creative act. Okay, it will be harder to make computers do this. The reality is usually more stable than appearance, i.e. changes more slowly. Now he starts making an analogy to science. So he talks about geologists and oil companies and astronomers being faced with the inverse problem. That is, you can observe the way things are. For instance, you can observe the surface of an area and look at the rocks and so on. A geologist might do this. But the question is, what's below that? What are the strata that you cannot see? If you're trying to find where oil might be, this is a key part of the inference that you would then need to use in order to decide where to drill. So he says their solution is intellectually difficult and computationally intensive, and human-level AI systems will also have to be able to infer reality from appearances related to them in complex ways. So what he's talking about here is seeing a phenomenon, but only partially. So you can only see part of it, and the rest needs to be inferred. So this is clearly challenging, still challenging. To see how important McCarthy's ideas are, it's worth considering the following. So he talks about various different entities and relationships that appear in, say, geology. But if we start to consider this in terms of science in general, I just started writing a list of various different entities. These are things that have had to be invented or proposed by various different scientists over the last few hundred years at least. And the list is goes on and on. I've just given a small number of things here that everybody will know about if they've had a science education. So atoms, electrons, nuclei, neutrinos, radio waves, planets, craters, all of these have been inferred from appearances and have been modeled by introducing the notion of an entity which cannot be directly observed, okay, or couldn't at the time of invention. And similarly, when we're thinking about these entities in the appropriate context, it's important to then start thinking about the relationships that hold between such entities. So for instance, force or pressure, the voltage, for instance, in an electrical setting, distances and speeds and all of the time and space related ideas, acceleration, inherited genetics, the idea of inheriting genes in biology, predation or electromagnetic induction, all of these, the entire list consists of inventions which have been done in the past by human beings. These have solely been done by human beings. And I would be very interested to hear of such a list that has been done by an AI system so far. So the fact that it's hard to find examples of that are already being proposed seems to indicate to me that this truly is a challenge. If we want AI systems to become supercritical or to go beyond appearance and reality, we need to be able to deal with the invention and introduction of concepts and basic ideas of entities. And the situation's not much different if we move from science to engineering. So here we have notions of bridges or canals, steam engines, airplanes, turbines, computers, and information. All of these things you might say, well, we know these exist. We know they exist, but the people who first built a bridge or a canal or a steam engine had to imagine the idea before they were able to make an example of it. And computers are an example of that. The relationships that then grew up in order to be able to decide how these systems interact include support, traction, relative efficiency, relative safety, relative information. So certainly in science and engineering, these are very creative areas where lots of entities and relationships have been introduced. And when we are taught as scientists or engineers, these are the bedrock from which we build our ideas. But science and engineering are still happening. These are things that are still being introduced and invented solely by human beings. So support from computational devices would surely be valuable in these areas. And if we look at mathematics, the situation's again no different. So all of the entities that are abstract in mathematics had to be introduced by human beings to this day. So the idea of a number, a set or a group, a function or a line, a polygon, matrix, lattice or graph, and various different relations, such as one thing being the square root of another, or an ordering among numbers, homomorphisms, subsets, and equivalents, right? So the human mind has been very fertile in these areas, and the people that have introduced them certainly live up to the ideas of supercritical thought, and thought that goes beyond simply an appearance, simply thinking of the way that the world is as it is, rather than how it could be, or how it could be rearranged to have some structure that is at first only imagined. Okay, so these sound like very difficult things to do. So, so the question here is, surely it has any have any advances been made in this area? So I'm going to give you a rather weak claim to that, but I'm going to use work that I know because I was involved in it, that I published last year in the Proceedings of the Royal Society A, on a system called DeepLog. And just to give you an idea of what that system did, rather than the details of how it did it. So this is an inductive logic programming system, and we're trying to learn a concept, which I'll call RVU up. And the idea in this paper was to question whether it's possible to learn concepts using only a single example. So the reason that this is interesting was motivated by the fact that this is not a very clear, there's no clear theory as to what the convergence would look like, or the probability of correctness of the hypotheses in the case that you've only got a single example. Most of learning theory deals with mixtures of positive and negative examples. In the case that you've only got one example, it's much less clear how convergence is achieved. But that's what was being discussed in this paper. So here's the example. We take a sequence of letters, A, L, I, C, E, and what we're given is the fact that that somehow is transformed to capital E, C, I, L, A. So I don't imagine that many people in the audience would find this difficult to see how that might happen, since you can see that that one appears to be the reverse of the other, but the difference is that the output seems to be all uppercase rather than lowercase. Now, in order to do the learning, there is some background knowledge, which is normal for inductive logic programming. What's different here is that a fixed set of background primitives was provided for a large set of problems, so that the initial set was always 63 library primitives. And down below, you can see the output that this DeepLog system gave. So what it does is it takes RVU up and it says that you need to break the problem down further after an initial call. The call sets up a stack. So this is one of the things that call one is one of the 63 primitives. It just sets up an empty stack. And then it uses a pop operation and then breaks it down further into uppercasing, and then a recursive loop in which you're popping and pushing until eventually you return when the stack is empty. So the whole process of putting the letters into uppercase and devising a reverse function is built by the system from a single example. And the theory behind this that was developed in the paper shows that with strings of the kind given, the probability of such a concept is very low, right? These are, because it's quite a large concept, the chances of this fitting by accident are very small, and evaluated here as 1 in 10,000. Okay, so what's interesting here from this respect to the questions, the fundamental questions that Turing was asking is the question about supercriticality. So you remember his quote in which he says that 1, 2, or 3 extra concepts are produced in response to a single idea. I mean, it's unclear what he meant by a single idea, but if we took here in respect to a single instance, then to some degree we see that here. So there's a series of introduced predicates which are built by the system in order to be able to construct the overall program. These are given rather arbitrary names, but we might and we might have to work on that in order to make them more interesting or more adaptable. But if we put a bit of effort into it, probably we could give names that people would understand. Okay, so that's at least a start, maybe not massive, you might say, but interesting. And it's a direction that could be potentially extended out in other topic areas other than this very simple one of reversing and uppercasing a sequence. Here's another one from the same paper, which was in this case, the same system was given an input-output pair of, again, in terms of sequences, but in this case, what was returned, or what would be expected to be returned, is a regular grammar. Okay, so here is the input. So we have A, B, C, D, E, F, C, D, E, F, G, H. Okay, so if you look at that, you'll see that there's a certain amount of repeating pattern around the C, D, E, F, which appears twice. And at the beginning and end are A, B's and G, H, and so on. So using exactly the same search and construction, the program here, the logic program, was built, and you can see how the various different sub-programs are built out of it. Let's say A and BC, ABC41. So you can see that, first of all, you need to recognize an A and then a B, and then it says that you need to do an ABC411, which then does this CDEF. So it actually recognizes CDEF, and then at the end, it terminates the recursion with GH. So you might wonder how CDEF suddenly appeared. Well, the system also, apart from building the main hypothesis, finds high-frequency sub-sequences within the input and turns them into auxiliary predicates, which are used if that compacts the overall description. So in this case, CDEF was introduced as CD, followed by EF, and CD is broken down into C and D, EF into E and F. And these individual letters, there's a function for each one of these to be consumed from a string, which is part of the 63 primitives, but you can see that this has already been introduced as an auxiliary in order to do this job. So the appearance and reality challenge, which Turing set, there's an element of this in the solution that you see here, in the sense that there's nothing in the initial sequence to show that there's something special about CDEF, but the system itself actually pulls out an entity, a kind of sub-entity, and makes it into an entity at the top level, which can then be used in building the overall grammar description. Again, the learning from one example issue means that this solution has very low generality and very high expected accuracy. These expected accuracies were demonstrated against graphs, and in fact, they fit quite closely to the outer sample accuracy that you get in these cases against independent data. Okay, so I don't think that anything that's been done here is definitive. I just think it's a start on addressing issues that are hard and that still, to a large degree, need to be addressed. And they are ones that were foreseen by some of the founders of artificial intelligence. So I think it's reasonable, if we're going to be using that term, that we should be looking at what those challenges were that as they imagined them, and seeing where we are as a measure. Okay, so I'm going to leave some time for discussion. But before I do so, I'm going to conclude. So Turing provided in his 1950 paper something I'm referring to here as the supercriticality challenge. Supercriticality is part of what he had in the text of that paragraph. But I think this is still a challenge, and we're barely touching on it with the examples that I gave. Similarly, John McCarthy, who named artificial intelligence as subject area, believed at the end of his life that we really weren't dealing with the hard issues in artificial intelligence, in particular something that he referred to as appearance and reality. And he thought this was a challenge right, at the end of his life. So I think if we can do these, there are great potential gains if we can make further headway in these areas, because they are related to extending, not just taking everything that is written on the web and producing it in such a way that we can provide answers, but introducing new ideas that have never been mentioned by, they've never even been named nor thought through. So you won't find all the answers out there. It's not there on the web to find, not even inferred on the web. But these concepts that have been devised in that way in the areas of science and engineering and mathematics are not the last say on what we need to know about in those areas. And what's required is machines that invent new concepts that allow us to explore those ideas as abstract models and potentially suggest experiments and tests on those concepts in the same way as these ideas are tested in science, in physics, in chemistry, and engineering, mathematics. All of these areas, we need additional support in the very hard task of coming up with hard ideas and things which explain some of the some of those appearances that we see around us. There are thousands of hidden entities and relationships which have been discovered over the last 200 years. I just gave a very brief and preliminary idea just to give you a kind of idea of what's there. Anybody who is educated in these areas has to learn these before they can start being even close to being competent. But that doesn't take them to a point where they can introduce new ideas necessarily. We need ways in which we can help human beings come up with ideas that are going to be important and essential for human advancement. So the area I've been talking a bit about is automated discoveries in ongoing science, engineering, and mathematics. There's no reason that it shouldn't also be in other areas outside of those, but these are areas which I'm familiar with, and I think that if we develop general mechanisms in those areas, they would be valuable in other areas as well. So just to finish, here's details which I'll leave up on the papers I was referring to. So Turing's Computing Machinery and Intelligence paper in mind, McCarthy's paper, which is in the proceedings of the ILP in Springer in 2006. And this is the paper I was referring to with the examples I gave on Deep Log, which is in the Philosophical Transactions of the Royal Society 2023. So I'm happy to take questions.
Thanks very much, Stephen. That was a very, very inspiring talk. I'll open up the floor for questions. I'm not sure what's the preferred way for the audience. If you prefer putting the questions in the chat window, that's fine. Oh yeah, there are chats now. So I don't know if you can, if you stop screen sharing, Stephen. You might see them yourself rather than
Okay.
having me read them out, which I'm happy to do, of course, but perhaps you'd prefer to, for instance, Robert has a question and you could just assume most audience members can see that, or all of them, and you could
Yeah.
just respond directly.
Okay, so Robert Blackwell. So AI is apparently being used for drug discovery and material science invention. Do these applications demonstrate supercriticality? Yeah, I spent a large part of my career involved in trying to do discovery in the area of drugs. I was even involved in a company at Imperial College where that's what we were doing. I don't think that the techniques that we were using would necessarily introduce completely novel concepts into biochemistry. I don't think that ever happened. What did happen was that we were able to identify certain molecules as having higher than expected binding affinity to certain proteins, for instance. That's the way that drugs typically work. But that didn't change biochemistry in the process. What I'm talking about is changes at the fundamental level of the definitions of a subject area. All of the examples that I gave are of that kind.
So, Stephen, I think Carlos has a question. I just realized, I think when I export the recording, it's unlikely that the questions will also be there. So if you could just summarize the question before you respond, Stephen, that might be good.
Okay, Carlos says, I have two questions. Number one, what is the relationship between supercriticality and open-endedness? And number two, what is the role of the environmental external output in supercriticality? Do you think a rich, complex environment is necessarily helpful in achieving supercriticality and coming up with new ideas? Okay, so I'll address the first one. What's the relationship between supercriticality and open-endedness? By open-endedness, I kind of guess that equates to an open world assumption in logic, and certainly that assumption has been dealt with in various different ways for a long time. So, for instance, McCarthy suggested circumscription as an approach to what is what can be claimed to be true. But what circumscription says is everything that we don't know about is not true, basically. Okay, so everything outside of the bubble we'll just assume to be false. That's not a reasonable way to advance science because you're simply closing off the avenues in which invention could happen. Supercriticality is kind of doing the opposite of circumscription. It's saying, I'm going to take this not as something that I can prove anything about, but I'm going to introduce concepts which will allow me to explore this topic further. I'm going to assume that the world contains things called atoms, and then I'm going to find out how those, what are the implications of that, and how can atoms be, how can they be viewed, and what are their relationships with others? Okay, so number two, what is the role of the environment external output in supercriticality? Do you think that a rich, complex environment is necessary, helpful in achieving supercriticality and coming up with new ideas? First of all, I think having an environment is essential, so that you do this essentially by something that is a form of learning. It's really it really struck me when looking at Turing's work that when he moved from being a mathematician to being a cryptographer, he suddenly realized that there was something that his theorems were not taking into account, that information carries on coming in, and you have to, the cryptographer has to keep on finding ways of figuring out what the hidden information means. And as a kind of model of what science is about, that tells you a lot. It tells you that you have to have a model of the world. You have to change that model of the world continuously in order to be able to advance. And you'll make errors in the process. That's what his previous theorems had demonstrated. You couldn't do this without making errors, but you advance by making those errors and seeing that they don't actually fit, that they're refutable, for instance. So I think that even with a not very rich description, you can make conventions. But if you had, the richer your environment is, you have to have rich inventions that go with it. Yeah, I hope that addresses.
Thanks, Stephen. While other questions come in, I had a few of my own. I mean, so since we have you for a few more minutes anyway, I'm playing the devil's advocate. As you might know, I'm very sympathetic, and also work on the kinds of things that you mentioned, including inductive logic programming. But if I'm playing the devil's advocate, you know, what I see is, if I consider applications in, say, finance, or I'm not sure, recommending books and so on by Amazon, what I'm seeing is that there's not so much the function of coming up with concepts, although of course that's what they're trying to do in a way, but they don't really care what these concepts are. So they're looking really to identify some sort of pattern that captures a functionality that they care about. So in that view, I mean, it's a very limited view of intelligence. I mean, one could argue, you know, this has nothing to do with the kind of intelligence that Alan Turing and John McCarthy were talking about, and that's one argument. But the more pragmatic side is, well, surely at that time, when Alan Turing and John McCarthy were looking into these things, that kind of idea wasn't there yet, or at least not the way we see it now. If that's a case where the concept is entirely implicit, and we simply care about the outcome, would it not make sense that a concept-based approach is somehow limiting? Because perhaps there are things we cannot say clearly, and by categorizing it and labeling it in some concrete way, we are needlessly abstracting the world in a sort of a dangerous fashion, because we're committing to some ontological concept that we don't want to refer to. It's implicit, it's in our feelings and our sentiments, and trying to capture that at a concept level seems problematic. I'm not saying machine learning solves this, but you see that, you know, having a signal-based approach seems to somehow move away from that, you know, that kind of commitment to a concept.
So I think that's that's very, yeah, I think that's very interesting what you're saying. The examples that I were giving were in areas in which the introduced entities and relationships are very crisp. I think that they are, you can embed them into mathematics, and you can make predictions, and you can just say what's necessarily the case and not. Okay. So not all subject areas are like that, and I was speculating that maybe one could move into other areas of the of the university faculties, and perhaps look at sociology, or perhaps start looking at arts or literature. And I don't think you can, in those areas, necessarily get the kind of crispness that I was talking about. The question as to whether people are inventive in those areas or introduce new concepts, I'm convinced that they do. And these concepts develop through discussion over time. And that's certainly of interest as well. I didn't cover it, but it has many aspects that are in common and many aspects that are not in common with the very kind of crisp idea of inventiveness. There's a new message that came in. Should I address that?
Yeah, there are two of them, one by Alex and one by Terence.
Okay, Alex Monaghan says, I struggle to attribute intelligence to machine where we can follow every step and see that that step is simply a statistical manipulation of data. No reasoning, no ontology, no model of the world, e.g. the illusion of a physics model in Sora. How do you think we should judge machines which we can prove to be just very powerful stochastic parrots? So this is I suppose this is different from what I was discussing, but I think it's also related to the question that I've just been talking about, that there's a very crisp version of this, and when you introduce concepts that, if you say, are very fuzzy in some sense, or only statistical, there's a degree of question as to whether or not these are just powerful imagined entities. The way I think the boundary there lies in science, lies in the necessity of defining experiments will actually refute predicted concepts. So the kind of Popperian idea of how to advance science by falsification. If we have clear concepts, even if they've been introduced by stochastic parrots, if they are testable, we're in the area of scientific discovery. If they aren't, it's hard to say what we're actually doing with those. I'm not sure if that's completely addressing your question, but I agree with the overall direction that you're going, that if we're really wanting to contribute to science and engineering and mathematics, we need to make these ideas clear, testable, and manipulable by mathematics. So the second question is by Terence Egbilo. Thank you very much. Taking a step back, why do we need science to be done independently by machines when we have not yet educated all the human scientists we could have, and have not yet demonstrated the limits of human-led scientific discovery? Good question. I'm not advocating human beings stopping doing science. I'm rather advocating the acceleration of human ability to carry out science. If just to take an analogy, this is a bit like when trains were invented. It didn't stop people from walking, but it did mean that if you wanted to go a bit faster, you could get on a train. And we already use a lot of instrumentation, machinery, etc., in order to advance science. We just don't apply it to aid our ability to consider new concepts. And I don't see a good reason why we should not do that, but I do see a good reason why we should avoid making technologies that make all of human existence irrelevant or pointless. I think at the very least, machines should be able to communicate ideas with human beings and collaborate with human beings. I think that's, to me, is essential if we're going to make advancements that are actually helpful to humanity.
Thanks, Stephen. There's a longer post by Alex. I don't know, Alex, if you just, I don't know if she's still around, but if you just want to speak up, or
I can see what Alex has written. So
Yeah.
Alex Laskarides, part of what makes one postulate that their hypothesis space, that the hypothesis space, I suppose, of possibilities is too small, is detecting inconsistencies in one's observations given that hypothesis space. So at the very least, intelligent machines need reasoning and need to detect inconsistency. When people know they don't know something, they typically ask an expert. So as a first step, perhaps we need machines to have the reasoning required to detect inconsistency given their hypothesis space of possibilities, which in turn trigger questions to an expert, all of whose possible answers will help improve their hypothesis space. And then the machine will need to adapt what it's learned so far that larger hypothesis with larger hypothesis space. That's not solving supercriticality, but it would at least harvest human expertise where needed. I would be interested to know if you think this would be a decent step towards intelligence. I certainly do think it is. I think it's in line with the notion I've just been talking about of collaborative activities between intelligent machines and scientists and engineers, etc. I think that there are various degrees to which and ways in which machines can be supportive or could be supportive. I agree with your point that being able to identify either contradictions or something close to it, that the probability of this being a coincidence is extremely low. If that can be done in a rigorous way, these will help us in identifying where the hypothesis space needs to be expanded. And it's typically expanded by, I mean, it's certainly in a logical setting, it's expanded by either introducing new entities into, the Herbrand universe, or new relations into the set of relations that we have.
Yeah, that's fantastic, Stephen. I have lots more questions to ask, but I think in the interest of keeping this within an hour, thanks very much, Stephen, for taking time. For everybody else who joined in, perhaps you aren't part of the mailing list, but if you haven't joined, please feel free to do so. But yeah, we'll have more of these, and we'll record this and put this up on YouTube if you want to follow up later. I suppose you could always send an email to Stephen. Probably get too many of those anyway, Stephen. Thanks anyway for this really inspiring talk. And everybody else, we'll see you the next time.
Great. Thanks for inviting me. Okay. Thank you.
Thanks, Stephen. Bye.
Bye.